do is we'll fantastic. So we will take questions during the conversation, but we'll mute folks so that barking dogs and the rest don't intrude. So, but at periodic points, raise your hand. Anthony may stop at various points, and then we'll you can unmute yourself and go from there. Anthony, thank you so much for joining us, and take it away.
Yeah, thanks for the invitation. It's great to be here. What a nice way to spend a Sunday morning. So I will look out for future ones. So I have a rather big and ambitious title here, and that will in fact be the nature of the talk. I'm a cosmologist, so this is just an occupational hazard to think about the very biggest questions. And I'm going to take you on that sort of a trip today. So I'll start on the biggest scale we have, the observable universe. That started, in a sense, in we can probe back 13.8 billion years when it was a hot, dense, nearly uniform expanding gas of elementary particles, had photons and protons and neutrons and neutrinos and dark matter and dark energy. And it was really simple. That was kind of it. It was a sea of those things, more or less uniform, more or less in equilibrium. But the standard cosmological model is given this amazing account of sort of the quantities of these things and how they evolved and then how they interacted and how they turned into the clusters, galaxies, stars, planets, and all these other structures that we see in the universe today and throughout its history as we can probe astrophysically. And the theories of the early universe, and especially the theory of inflation, which I've spent a good chunk of my career studying, have given us a really nice and predictive account of where that early medium got its properties. That is how we started out with, how the universe got to be this uniform-ish sea and equilibrium in a big expanding space. And the universe started out with this set of things, which you can see on the slide here, these basic constituents. But all of those things in the early universe were interconvertible with each other. So you can, at high enough energies, all of these things can turn into each other. And so the early history of the universe is kind of a tale based on the
dark matter.
Not clear.
Dark matter's there.
Yes.
Negative energy. Yeah.
Oh yeah. Well, yeah, dark matter can certainly turn. I mean, assuming dark matter interacts with something at all, it at high enough energy can be converted into, all of these things can interconvert. So the very early history of the universe is kind of the tale using fundamental physics of how these things, how we ended up with these relics from that very, very early phase of just these sorts of constituents. And quite interestingly, there's a part of that tale in which all of the observable stuff in the universe in some sense has zero energy, that we started out with some positive energy and some negative energy. The negative energy is still around in the form of gravitational potential energy associated with all this stuff. The positive energy is all the stuff. And so it's a sort of amazing story that the universe could have started out with no stuff, and through this process of inflation generated all of these different constituents, all these huge amounts of matter that we see. And then from there,
Bill, it's you're.
I'm sorry, I'm trying to get out.
Okay, thanks.
Thanks. And then from there, evolve into the universe that we that we see.
I just finished a nice conversation with Jody,
Oh,
half an hour, and she's looking very recovered and
okay.
feeling well.
Bill, are you trying to join the concepts meeting?
I took my power to mute Bill.
Oh, good.
So Barry, you might want to mute us and then just let us turn back on when we have questions.
Okay, I'll do that. I'm going to mute all here.
And you're going to have.
And then Anthony, you'll unmute yourself, and Pete.
There we go. Okay, So the universe we can think of as being endowed through this very early process with this huge amount of stuff, particles and fields of these various different types. But it also started out with, as it turns out, a huge quantity of something else, which is only sometimes talked about, which is an immense quantity of information. So this might sound a little odd in the sense that we think of information as like complicated things. So we have digital information, we have information processing in the mind or in the brain and in computers, and we think of information something very simple like this uniform sea of homogeneous gas as being information free, but it wasn't actually. So something that has been pointed out over the years by Roger Penrose and a number of cosmologists, and I agree with, is that if you include the space-time degrees of freedom, that is the scale and the smoothness of the universe, then the fact that the early universe started out in this small scale and very smooth state means that it was very, very low entropy and very, very information rich. So information you can think of in a very concrete mathematical sense as the flip side of entropy. When you have high entropy, high uncertainty, high randomness, you have very little information. When you have low entropy, you have lots of information. And the universe started out very low entropy. If you think about it, it sort of had to be that way because the entropy increases with time. That's the second law of thermodynamics. So as you go back in time, if you hold on to that view, the universe had to have less and less entropy and more information. But I think it's, so the universe started out with this huge amount of information, but I think it's safe to say that unlike all of the stuff, nobody has a real compelling vision as to where all this information came from. I think it's a central question in cosmology that rarely gets talked about. But however it arose, there it was 13.8 billion years ago. And since then, it's been kind of transformed by physical processes into different forms that we can identify as reservoirs of information, or in the thermodynamic parlance, free energy. This is useful information that we can do things with. So, for example, this low entropy, uniform, chemically simple gas that the universe started out with, the baryons, that is the normal stuff, started out like 75% hydrogen, 25% helium, a smattering of other things. This is much more chemically simple than it could have been. This is not actually the state that the universe wants to be in thermodynamically. So if the universe is relatively cool, the state it wants to be in is mostly iron and an admixture of other things. The universe didn't start out like that. It started out chemically simple. And the fact that it started out uniform and chemically simple and got lots of volume allowed for the well-spaced structures that are hotter than their environments, like stars. And the chemical simplicity of this matter allowed stellar nuclear fusion, which provides high energy photons that can shine on all over the place, including on planets. So we have stars, which are these beautiful reservoirs of low entropy stuff, that is reservoirs of information in a sense, that are out there shining and providing that information to everything around them, including us here on Earth. They're really pretty miraculous. This is a movie I downloaded of 10 years of the sun's life in 1 minute. So it just burns and burns very steadily, pumping out all of this information year after year after year. So we would have to watch this movie 500 million times in a row to get the view of the sun as it actually has shown. And of course, there are all kinds of little variations and instabilities in the details of the sun, but the fact that it for 5 billion years has just shown in this amazingly uniform sense, that has allowed these things to happen on Earth like us. So it allowed this to happen on Earth, this chemical process that we call life, that can reproduce and evolve units that metabolize. So they take this information or free energy and they use it to maintain their own structure, sort of in accordance with the second law of thermodynamics, which holds in general, but they're able to hold their own sort of internal information and low entropy by using the information in the environment and expelling kind of high entropy waste. So they're a sort of unique thing in the universe that can do this for long periods of time to maintain their own structure despite the edict of the second law of thermodynamics that the entropy has to increase. We call it metabolism, this process, but I think it's not unreasonable to think of it as a sort of information processing, where the processing that it's doing is taking the food that holds information into itself, and to call this a computational process. It's interesting to note that, you know, when we talk about wanting to have energy, like gasoline contains energy, or coal contains energy. Of course, it's not really energy that they contain. Everything contains energy. Everything is energy. It's very uninteresting to have a certain amount of energy. It's all about the accessibility of that energy, and also all about the low entropy form that energy takes. So what's useful about gasoline is that you can easily liberate the energy that has by increasing entropy, explosively, literally, if you want. And so what we really talk about when we talk about fuel, useful fuel for things, is that they're information rich, and that information can be liberated in a very simple, straightforward way. And that's what life has gotten very good at. It's good at finding information rich substances out there with accessible free energy that it can then use for its own purpose of maintaining itself and reproducing. So this sort of arguably computational process does things that are very distinct from everything else in the universe, that especially that physicists tend to study. It has goals: to stay alive, to acquire resources, to reproduce. It has intelligence, if you broadly construe intelligence as kind of perceiving and modeling the world, and the organism in relation to those, to the world. And it has goals. It has agency. That is, it in some sense takes the information it has about the world and its goals that it has and chooses actions to accomplish those goals. So life will decide to go this way rather than that way. If there's an amoeba in one direction and a source of food in the other, that's a choice in a sense. It's somewhat automatic, obviously. There's no deep philosophical thought going on in the microorganism, but it is a choice. It's taking information from the environment and moving toward a goal of survival, and doing one thing rather than another. So it has intelligence in that sense, all the way up through the chain of complexity to the sorts of intelligence that we humans enjoy. And this is something really that's very different about life than the rest of the physics in the universe. The best explanation for why a star, does what it does is, well, this is what hydrogen gas does when you gather it into a big ball. You run the laws of physics, you come up with a stellar model. It tells you how the density varies with the radius of the star and the temperature and so on. That's why the star shines like it does. When you ask, why does this mitochondrion have the particular structure that it does? Well, it's because its purpose is to store and create energy. That's what it does. That's why our cells like mitochondria to exist in them, because they provide us energy. And so it's a purpose-driven explanation. Of course, you can also talk about all the little atoms and molecules that are in it, and they're following the laws of physics, but it's a terrible explanation for the structure of a mitochondrion. If you want to know why a mitochondrion works the particular way it does, the explanation is in terms of goals and functions, and not so much in terms of the wave function or the forces between the atoms. Those are still true. Those, of course, constrain what the mitochondrion does, but it's a terrible way to explain very little explanatory power over the details of what it is doing. So life is very different in this sense than the rest of the stuff in the universe. Those different sorts of explanations become useful ones. Now, we don't have any evidence that this process, life, exists anywhere else in the observable universe, period. We just don't have any. There are a lot of people who say, yeah, but look at how many stars there are, right? There's so many stars out there. And now we know there's so many planets out there. So of course, it's got to be the case that life is out there as well. And that may be true, but I think we really can't know. In particular, probabilities, especially of chance events that involve many, many parts, can be really, really, really small. So no matter how big the numerator is, how big the number of planets and pounds of stuff that there are on planets, if you multiply by a small enough number, it's going to be less than 1 in the observable universe. And in particular, it's possible, we don't know this, but it's possible that the origin of life required some random generation of some very, or even rather complicated thing. So this is RNA polymerase. This is the enzyme that helps RNA reproduce. If the origin of life required something like this to come together by chance, or even something much, much smaller than this, much, much simpler than this, then there's no way it would have happened twice in the observable universe. The numbers are just astronomically tiny, 10 to the minus, 10 to the 50 and things like that. Wouldn't happen twice. So I think we don't know whether it's out there. We just know that it's here. And that I think is an important point to keep in mind. We don't know that there's some backup. If we, as I'll say later, screw up things here on Earth, that may be it for life, at least in the observable universe. And that would be a gigantic shame. That we can't necessarily count on all those aliens out there going forward and making the universe interesting for us. So that's life. And then an astonishingly short thousands of years ago, life created something, again, new, technology, complex, deliberately designed physical systems that help us achieve our goals as living things. We also have no evidence that this process, technology, exists anywhere else in the universe either. But here it is. So we can ask, it's really new on the cosmic timescale of billions of years. It's only 1,000 years old, this technology. It's a brand new thing. We're sort of at the state technology-wise that life was at, in the first few minutes 4 billion years ago, maybe the first 1,000 years, 4 billion years ago. Very, very new. Who knows what it's going to turn into? Nobody does, is the answer. We have no idea. We can't know what the future of life and technology is, but science is fundamentally based on both explaining and predicting. So we as scientists have to at least try. And there are things that we can make some predictions about. They're just, more or less precise than other predictions we might want to make. So what can we do? Well, one thing we can do is look at the long-term future of the physical universe. We have good ways of understanding the universe in terms of the stars and planets and galaxies and so on that make it up. And here, the news is all essentially good in the sense that there's lots of time, lots of the things that we enjoy that will stick around for quite a while. For example, we can see how often there are astrophysical and other sources like geological sources of mass extinction that kind of might wipe out humanity, or at least a big chunk of it, even wipe out like most of the life on Earth, but they're very infrequent. We probably have, 10 or 100 million years until the next one of those hits us. So that's good. Life on Earth is relatively stable. To what degree we needed those sorts of extinctions in the past to make life as interesting as it is now, I think is unclear. That may well be. But if they were too frequent, things would be very boring, and we'd probably get blown back to microorganisms over and over again, and we wouldn't have the nice complex life we have now. So we've got that much time. We've got like 1 billion years until the Earth gets too hot. The sun is getting slowly brighter, and it will become uninhabitable here. We might be able to do something about that. One of our ex-Santa Cruz colleagues, Greg Laughlin, and others worked out an ingenious method of moving the Earth steadily farther away from the sun by very carefully nudging asteroids to come and interact with the Earth and give some of their energy to the Earth to move it out. But we've got a while to figure that out. We've similarly got 1 billion or 10 billion years of stability in the solar system. The early solar system was a rather chaotic place, and there were probably multiple planets that got ejected. The moon probably got formed by an almost Earth-sized planet running into another almost Earth-sized planet. So it was a bad place, but lately it's calmed down, and for the last billions of years, it's been very, very stable. That'll go on. The local group of galaxies will stick around for well, for a very, very long time, but we'll get to see beyond that for about 100 billion years. So our local group of galaxies, because of dark energy, will eventually get sort of isolated, but in like 100, in about 100 billion years, but it will continue. Stars themselves will continue for about 10 to the 14 years. So those will be low mass stars and kind of not once as bright and interesting as the sun, but there's no reason we couldn't have life around low mass dimmer stars. It just might be a little more expensive to use solar power and so on, but just get a planet that's a little closer. The galaxy itself will exist for 10 to the 20 years. It will be at late times made up of stellar remnants and black holes and things like that. But even around the black holes, you could imagine still running computations and life and so on. We might run into a bit of a wall when protons start to decay and cease to exist. But I think even there, we don't entirely know. And technology will have gone a long way in 10 to the 34 years. So I think there's the good news is in the sense that the universe is only 10 billion years old, but actually a lot of its history is in front of it. And so there's plenty of time. There's this sense in the air, there's this kind of zeitgeist that like we're coming to the end times. I think that time, that feeling has been around for a lot of human civilization. There's this nice, there's something that people like about feeling like we're at sort of the end of history and it's all coming to a close soon. That is possibly true if we make it of our own making, but if we don't, there are just oodles of time left for all kinds of good stuff to go on. I should stop here because I've been going without getting any questions, and I'd love to hear any thoughts or questions anyone has.
So I do have a question, Anthony. This is Pete. Right now, the human condition seems to be big arguments between people who are worried about the next paycheck and want to keep burning coal and elect Donald Trump president, and, or the equivalents around, and folks that are worried about billions of years in the future. And I'm wondering just if you thought about that conflict in the 10 to the 1 years.
Yeah. So I think I would be a little less optimistic about how many people are thinking about the long-term future than you are. I think I like to think about the long-term future. There's a few other people who like to think about that, but I think those people are rather underrepresented compared to the people who are thinking about now, or the people who are thinking about 1 to 5 to 10 years from now. That is certainly an important time scale. But I think there is something, you come at things from a somewhat different direction when you do look at the very long time scales. And I think that doesn't need to be the dominant perspective. I don't think it probably should be, but I think it is a useful perspective, and that some people should be thinking that way. Yeah. In the same way, on a day-to-day basis, you think about, what am I doing today? What am I doing next week? What am I doing next year? You don't often spend time thinking, what am I going to be doing 20 years from now or 30 years from now? But it's good to sometimes spend a little time thinking about that, right? Because it does add a certain perspective. It does reconfigure, I think, the way you're thinking about those shorter term issues. So that's my feeling about it.
Other questions? I will say I thought that your this notion that we may be more unique than people think was compelling to me. It is certainly true that the cellular experiment, we've had talks about how cell walls led to a billion years of experiments that led life, and it's certainly true that replicating that exact sequence of experiments and outcomes is a pretty rare event.
Yeah, I mean, I think there's a contrasting point of view that says matter naturally likes to do certain things like find ways to be stable against entropy increase, or increase entropy production, or that there's just something like built in and inevitable about forming complex systems like life. But I think we don't know that. You
Yeah.
know, we have no really good evidence either way. And if it, I think the point that I'm making is just that if there is some kind of random chance involved, as soon as you admit that, it's easy for that random chance to be so infinitesimally tiny that it's just going to overwhelm every other number in the problem.
Yeah.
And that's what I think it's hard to convey sometimes, how small those numbers can be as soon as you get even tens of particles together.
Yeah.
In some particular way.
Maybe,
I have a sort of a simplistic question. Does this possibility of multiple universes affect any of these predictions?
Well, yeah, I don't think I predicted anything yet exactly, but I think
Okay.
I think multiple universes are probably out there in some sense or another. So there are lots of different meanings to multiple universes. It's almost certainly true that just the observable universe is not the only universe there is of the same size. There are probably at least, you can pretty formally show, in fact, it's amusing, that there are probably at least millions of times more volume to the universe than the part that we see. That's like a bare minimum. If I had to bet, I would bet that the universe is actually infinite. And so there's just a lot of stuff out there. And then the question is, how diverse is that larger universe than the one that we see? Is it all pretty much the same as what we see here and just kind of more of the same, but on larger and larger scales? Or do those other regions have very different properties than the ones that we have here? Some of them amenable to life, some of them not. So there are interactions between that question and the question of life, in the sense that there could be lots of regions of the universe. Oops, let me go back. There could be lots of regions of this bigger universe or a multiverse in which the laws of physics just don't let anything complicated happen. So you can have a universe. So if the universe that we're in had just 10 times more vacuum energy, it turns out that nothing basically interesting would have happened. Maybe 100 times higher. Nothing interesting would have happened. We just would have kept with a sea of simple gas. No stars would have formed, no galaxies, and so on. So that would have been a pretty boring universe. Probably no life in it. Probably nothing, wondering what's going on. So it could be that if you want to ask the question, why is it that the universe is constituted such that life can occur? The correct answer to that might be luck, in the sense that there were lots of different universes that rolled the dice in different ways, that have very different properties. Very few of them have properties that would allow life to arise, but of course we're in one of those. And so we see nice hospitable conditions around us. This is often called the anthropic principle, and sometimes has a bad name, but I think it could just be the right explanation for right answer to certain questions of that type, like why is the universe so hospitable to life? That could be one of the answers. On the other hand, the universe is hospitable, but not that hospitable to life. It does seem like it could be a little warmer and cozier. So you can go either way with that.
maybe one more question. You sort of taken information as the fundamental building block of the universe and kind of looking at things that way. And I'm wondering where knowledge fits in that. Is knowledge some sort of really energy efficient way of replicating stuff?
Yeah, that's an interesting question. So I think I view information as, one of two core building blocks of understanding what's going on, the other being energy. So I think, neither one is necessarily the fundamental thing, nor are both of them combined. They're fundamental is a word that I've become more and more suspicious of. But I think it's a very useful concept in understanding the kind of basic stuff that lots of things are created out of, where the energy provides the stuff and the material existence, and the information provides the structural existence of them. Now, information has certain technical definitions. And one of the things I've been very interested in is understanding, what those definitions are, how they relate to each other, how they relate to definitions of entropy and so on. And that's been part of my work lately. Knowledge is less technically well defined, right? So I think there are definitions in terms of, is that information useful? Is it held by, an agent that is doing things with it and so on? So is it information that can allow you to distinguish two different situations from each other, or allow you to make choices, like the sort of information that goes into agency? But I don't think there's really an agreed upon definition. I would say it certainly is, by most definitions, I would say knowledge is more associated with the kind of systems like living systems or mental systems that are more rare, whereas information can be associated with any natural process in the universe. So the universe can have lots of information, but I would say it probably didn't have knowledge by a reasonable definition until there were, at least animals and probably at least microorganisms, maybe animals, maybe people around to have that knowledge.
Okay, thanks.
Okay, so I talked a little bit about the natural universe that will exist long into the future, but that's the easy part, because stars and galaxies and black holes and the like, although it's taken a lot of work to understand how they operate and what they do, they're actually very simple compared to the more complicated things like life and technology, which throw a big wrench into the gears of predictions like this. So I want to give you a fun example, which is several years ago, I started an online platform called Metaculus with the idea of soliciting and aggregating and keeping score of predictions of all kinds. And it's since grown to thousands of questions and many tens of thousands of predictors, 500,000 predictions on things. And it works quite well in the sense that it assigns probabilities to future events, and those probabilities are pretty accurate. Of course, it's not a time machine or a crystal ball that can tell you exactly what thing is going to happen. But just like flipping coin, you don't know necessarily what the coin flip is going to be next, but you do know that it's going to be 50-50. And even knowing what those odds are for lots of things is useful. So you can check out metaculus.com. It's a fun thing to look through in terms of the detailed things that are being predicted. So here's one that is kind of an amusing one that we started early on in the site. Will there be a total solar eclipse in 2522? Okay, so that's around 500 years from now. So what's your prediction as to whether there will be a total solar eclipse in 2522? I'll give you a hint. Here's the catalog of solar eclipses from 2501 to 2600. And if you look in the lower left, you'll see one predicted for 2522 with total solar eclipse. It's like 7 minutes long. So, this type of prediction is really, really good. We've gotten excellent. That's why we have these tables for 500 years from now, down to the minute of when solar eclipses are going to happen. So let me show you the Metaculus prediction for that. 95% or 88%, depending on whether it's the community or the Metaculus prediction made out of the best predictors. So you might think, that's crazy. Like, this system is clearly broken. The eclipse is going to happen. The astronomers have predicted it. There's nothing, there's no uncertainty in the problem astrophysically that would lead to anything like a 5 or 10% uncertainty in this occurring. So what's going on? Well, it's not broken. This is I would claim, reasonable prediction. Why? Because 500 years is a long time, especially when technology is concerned. And a lot of predictors actually gave a non-negligible probability that humanity may have engineered the solar system enough to interfere with eclipses. And if you think about that, it's clearly true that the dominant part of the uncertainty is not what's listed by NASA, uncertainties in the Earth's rotation, as it turns out, but what we, living beings, will be up to in the meantime. For example, the current gross domestic product the current world domestic the current gross world product, if the word's right, is something like $100 trillion a year, right? It's been growing at 3.5% for at least 100 years or so. If you imagine, and this is not necessarily the case, obviously, but if suppose you were to imagine that it grew at 3.5% for the next 500 years, that's 30 million times larger gross product for the world. What would that look like? It's not going to fit on planet Earth, that's for sure. So either we're going to stop growing that fast, or we're going to move off of Earth into the rest of the universe. And if our economy is 300 million times larger, you can start to imagine things like, oh, that moon is looking kind of useful. There's a bunch of material there. What could we do with that? So the dominant uncertainty in what's going to happen in the long-term future of the universe has nothing to do with physics, I think. It has everything to do with what life, technology has in store for it. Let's look at another somewhat disquieting question that may be related to this one. This is a question on calculus. Is there going to be human-machine intelligence parity by 2040? And the prediction here is of order 35 or 40%. So what does intelligence parity mean? The question defines this specifically as a machine system that would outperform a set of physics, computer science, and math graduate students. So it's actually graduate student machine intelligence parity on a 2-hour exam composed to like adversarially advantage the humans. So this is a very strong test. If we had a machine system that could perform better than a trio of grad students on a 2-hour test that was chosen to be easier for the students than the machine, that's going to be a very impressive machine intelligence. And 35 or 40%. And I don't think you're going to find a more credible or accurate number than that one. If you ask AI researchers, or if you do surveys of them or all kinds of different methodologies, you don't get things that are terribly, terribly different from this. So depending on who you ask or how you define it, this high level or general or transformative artificial intelligence is a ways off, but it's no longer, I think, some like could be hundreds of years from now dismissible fantasy. In the last 5 years alone, we've seen techniques, reinforcement learning, for example, developed so that a single basic architecture that is just playing by itself has become superhuman at any full knowledge like Go and chess game, and many hidden knowledge games like StarCraft and poker. So here, for example, is the training of what was called Alpha Zero. This was you may remember the AI company DeepMind back in 2016 became or had developed the strongest Go playing system in the world, defeating the player Lee Sedol in 2016. So Go was kind of defeated by this AI system. Then a few years later, they developed something that didn't just play Go, but played pretty much any game, and didn't use any data from actual Go players in its training. All it was given was the rules of Go and the ability to play Go against itself over and over again. And over 30 hours, it went from basically didn't know how to play Go at all, or terrible, up to the best in the world. So 30 hours of self-play by this system. So this is a pretty amazing thing. As Max Tegmark, my colleague, likes to put it, AI, it can't just now beat us at playing chess, but it beats us at creating chess playing systems. So it's better than an AI researcher at creating a chess playing system. And essentially any game now that can be put into a form where everything is known and there are a specific set of rules and self-play is allowed, an AI system can just learn how to play that game better than any human. So this is a genuinely new and big deal in the world. Go was taken to be sort of the thing that AI couldn't do. It took human understanding and insight and intuition, and it's fallen along with a lot of these games. There's a system called GPT-3 that was developed a year or two ago, and it's a language model. If you haven't seen it, it can produce an amazing facsimile of intelligence and understanding, and frankly, write text that reads better than a lot of pieces by college undergrads. So unfortunately, I think we're in for an interesting time as, for example, university professors, where you can genuinely, not just copy text from someone else that's been around for a while, but you can generate text by a machine system that really does read better than most undergrads' text. It does fall apart as you read it. Things start to not make sense over long periods of time, and there are weird things that a human wouldn't write. But a lot of those aspects apply to some undergraduate writing as well. By humans. And even more weirdly, this system that was trained just to basically create text, as it turns out, can add numbers. You can ask it, what is 12 plus 24? And it knows how to add 12 plus 24, even though it was never taught how to add 12 and 24. So there are signs that just by sheer sort of volume of information and training, it's generalizing to do things that it wasn't explicitly even trained to do, let alone explicitly shown how to do. Moreover, there are certain problems that were thought to be quite hard. For example, combining different sensory modes like vision and text that are turning out to be almost non-problems. So this is a system that came out less than a year ago called DALL-E. You write a caption and it generates a bunch of pictures for you. So what I wrote was an illustration of a baby penguin and a cape playing on a grand piano, and it just churned out all of these different things. If I had said a old elephant in a tutu playing the saxophone, it would have generated 15 of those things for me too, and they would have looked like this, and I could have asked it for it in the style of a photograph or a Matisse painting, and it would have generated those too. It's really quite crazy. I'd encourage you to just Google DALL-E. They have a little thing where you can put your own prompt in, or I think you might have to pull from a pull down menu rather than type it in, but you can try out combinations and generate your own. And it's fun, but it's also scary in a sense, because this was done not by, I don't want to minimize the cleverness of the people who did this, but more or less they just trained the system on lots of images and text that were related to them in one system, and it was then able to go from text to image. And there's another similar system that can go image to text, put captions on images. So in all, AI as a field for a long time has been characterized by sort of over optimism, in the sense that, oh, these things should be really easy to do, and let's just make an AI system that will do that. And it turns out over and over again to be harder and harder and harder than people thought. And systems that they thought would be general turned out to be really narrow and brittle and kind of go astray really easily. And we're now in a regime where systems are showing surprising generality when you expected them to be narrow, and sort of new features and new capabilities that go beyond what were expected out of them. So processes become sort of surprisingly fast rather than surprisingly slow. And this is a huge change.
Anthony, can I ask one about this?
Yeah.
So when they're drawing a piano, for example, is this an original drawing by the machine, or is it going back into a library and picking up images of pianos?
Well, it's hard to say exactly what. A little bit of both, in the sense that it's not literally taking an image of a piano like a GIF file and combining it with another one, but so it's extracting ideas about pianos from probably literally millions of pictures of pianos, just like we do. So what do you do when you draw a piano? You're not exactly copying some other piano picture unless you're literally doing that. You've got some idea of piano in your mind. You know that it has legs, that it's got a thing that goes up, it's got keys. These are things that you know from all the pianos that you've seen. And you start to draw and you kind of combine those elements into something. And I think something pretty similar is happening here. None of these pianos I would bet that no one of these piano pictures, certainly pixel by pixel, exists in an image somewhere. So it's not just cutting and pasting. It's doing much more than that. And you can see this in other things that it will generate. There's no picture of a piano as drawn by Van Gogh, but you can ask this for a picture of a piano in a Van Gogh style, and it'll do that. So it's very much more like a human neural system in that sense than previous systems that you might imagine just Photoshop, like cutting and pasting things together. Any other questions? Okay. So part of what has driven this progress is Moore's law. It's not quite what it used to be in the sense that the rate of doubling of computer performance is slowing a bit, but it's still pretty exponential. If you look at these two plots, one is for the sort of amount of floating point operations per second as in the top most powerful computers. So it's gone pretty much exponentially increasing. That is, since this is a log on the y-axis and linear on the x-axis plot, these straight lines are exponentials. So it's gone exponentially up from the early 90s at least, and probably farther, up until fairly recently. And the one on the right is energy efficiency. That has slowed a little bit, but is still going exponentially up, even up to this day. So this is, exponentials are always interesting in the sense that they're interesting and they're tricky in the sense that when something's exponentially increasing, it's not that noticeable for a while, but then suddenly it's really, 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 really noticeable. And I think that's part of what's happening with artificial intelligence and machine learning. For a long time, the computation was simply underpowered to do anything interesting in machine learning. Suddenly, the exponentially has hit the point where it is doing something interesting. And now, because the exponential progress is continuing, that's going to suddenly become really, really important over the coming 5, 10, 20 years. So I think that's where we are with machine learning. And one might also think, and I think we don't know to the degree to which this is true, that really getting high-powered AI systems might require some really deep fundamental growth in our understanding of how intelligent systems work. Right? So there's been a long time, I think, where there was steadily new concepts in AI. The neural nets there were expert systems and then neural networks and single layer and then multi-layer and lots of techniques that have been building up over the years. And you might imagine that they're just core components of how intelligence works in human minds or other minds that we don't understand yet, and we won't get really high-powered AI until we do understand it. And that could take a long time. Quantum gravity has been sitting around for decades with super smart people thinking about it. We still don't know what it is. Could well be that AI is the same way. And I think we don't know, but there is evidence that at least at some level, just continuing to turn up the crank of how much computation we use is still paying off dividends. So the plot on the left is indicating how large the largest computational models are. So this is in billions of parameters. So it's sort of the numbers that go into the model that are, those parameters are being adjusted and fixed through the training process. So this is like for GPT-3, there were 175 billion numbers that got chosen through the training process by imbibing more or less everything that they could get their hands on in the internet, and spending a huge amount of computation, tens of millions of dollars, if not hundreds of millions of dollars, just of computation to train this model. Now there's a somewhat bigger one that just was launched like a couple of weeks ago, I think, called Megatron. not disquieting at all to call it Megatron. So this new one has come out. And the reason that people are spending more and more money and time and energy on making bigger and bigger models is that it seems to work. So what's shown on the right is a set of language model performance tests. So these are specific quantitative tests that are done. And you can see that the test loss, that is kind of how inaccurate they are, just keeps steadily decreasing as you add more computation or more data or more parameters that you're doing. And so there seems to be no sort of flattening off of the increase in machine learning capability as you keep adding more computation or data size or parameters. So just more of the same at the moment keeps making things better. Now, it may be that they hit a wall, or it may be that there are just things that are not captured by any of these tests. But at the moment, more is better seems to be holding. And I didn't mean that as a pun, but Moore's law seems to be underlying just better and better and better machine learning systems, even without that much extra like know-how or techniques. At the same time, those extra techniques and people, like very smart people working on the problem, also has increased. So the top AI conferences used to have like hundreds of people, I hear. Now they have tens of thousands of people after limiting admission. Google DeepMind, explicitly a company trying to build artificial general intelligence systems, has of order 1,000 well-paid top AI researchers working on the problem all the time. And that's a lot of firepower, even for the most difficult of problems. I imagine if we had, how does that compare to the effort in quantum gravity over the years? Probably larger. It's hard to say. There aren't that many people working on quantum gravity around the world, but it's probably comparable. And so if you want to argue that AGI is going to take many decades, you're arguing that it's like a much harder problem, I think, than quantum gravity, for example. And there aren't that many problems that have turned out to be that hard. So it's probably coming. It's exciting in the sense that if we define intelligence as the ability to achieve goals and sort of choose well to make the right choices to achieve the goals that we want, then like almost by definition, more intelligence is better. It lets us achieve our goals more accurately and quicker and so on. And so there are huge potential gains in predicting and designing complex systems and intelligently processing vast amounts of information, developing new science and technology and doing science, and so on. So there's a huge upside to all the power that these machine learning systems will be bringing. It's also quite scary, I would say. There's like no chance that the world will be anything like the way it is now if we're not the most intelligent things on it. And most of the very different ways the world can be are not so great if you think about it. There are lots of ways that the world can be, and many of them are bad. So I think the world staying pleasing to us will hinge on high-powered AI doing what we actually want it to do. And there are reasons to be rather pessimistic about this, if I'm being honest. The reasons one might worry about high-powered AI systems are kind of similar to the reasons one might worry about any high-powered agent that has a simple goal. So think for a moment about a corporation, right? If the corporation's goal is just maximize shareholder value, that's it. What does the corporation do? Well, we know that it does all kinds of stuff that aren't exactly evil, but we as a society or individuals don't really want it to do. And so we have to constrain corporations with all kinds of laws that we have to pass in order to keep them from just, say, polluting the environment and exploiting workers and all these things. Not that this is just what they will do in maximizing one particular thing, which is shareholder value. So in general, if you have some complicated function of many variables and you try to maximize it, then the place where that maximum occurs is going to put a lot of those variables at rather unpredictable and kind of extreme values. It's not going to care about anything other than just that thing that you chose to maximize. And corporations kind of work this way. Another thing you can worry about is if you think about a corporation that's trying to just maximize that number, it does other things too, like it will try to develop power, for example, to influence Congress or get legislation passed. It will become hard to, it will try to preserve itself. A corporation won't want to go out of business, so it'll do what it takes to stay in business and so on. So once you have one goal, there are lots of other goals that you will have to develop in order to satisfy that one goal. You know, if your goal is just, Stuart Russell's put it this way, if you have a machine that, or a robot say, that just wants to make you coffee, that's benign enough. But it knows that you can't make someone coffee if you're not operating. And so that machine will naturally, if it's smart, if it's effective, if it's good at making coffee, not want to be switched off. Not because it inherently wants to preserve itself, but because you can't make coffee if you're switched off. So if you want that machine to make coffee and be switch offable, you're going to have to add a second goal, which is to be switch offable, and so on. So you can think that you're going to have to start adding lots and lots and lots of goals or constraints on a complicated system to keep it from going awry. And we've seen this in spades in our high-powered agential systems of corporations, for example, and other high-powered groups. If the goal is simple, there are lots of constraints that we have to put on them. And so my concern about artificial general intelligence is, what if it's a corporation on steroids, like much faster, much more effective than a large corporation, but just as simple in the sort of goals that it pursues? We're going to be in big trouble. If you'd like to stay up at night thinking about this and worrying, here are a few books that I can recommend to make you concerned. In order, I would say these are displayed in order of terror, from the alignment problem, which is more prosaic, up to superintelligence, which will make you feel like the future is hopeless. I think it isn't, but if so, you can pick something nice and in the middle if you want to get a good sense of the problem. So, and I see that I'm getting low on time, but I'll say a few more things. So AI, of course, is not the only transformative technology coming our way. This is a plot of the cost of sequencing a human genome. It's gone down exponentially, although it's leveled off a little bit recently, and is now at the point where this can be done fairly cheaply, less than $1,000. There are also technologies like CRISPR that are allowing us to much more easily modify genomes of creatures. And so, we're soon going to have an ability to both understand and manipulate, well, we already sort of do, genomes of living creatures. The thing that has really held us back, aside from not having those two parts, is really understanding what the genome is actually doing. You know, I think most people are now seeing the genome more as a complicated computer program than as just a set of data, in the sense that it's there's a huge amount of complexity in the way that a given genome gets expressed through the life of the organism into a particular phenotype. But we're starting to make progress there too, and part of this is machine learning powered. So this is another thing that has come out of DeepMind that created the Go playing computer. A big open question for a long time has been how to understand how a sequence of proteins, a sequence of amino acids will fold into a functional protein. This is called the protein folding problem. It's been sort of stalled for quite a few years. You can see the gray bars there, not much progress. Suddenly, in the last 3 years, there's been a gigantic progress until the problem is essentially solved. And it's a machine learning system that has done that. So a system that is trained on a large amount of data, but the same basic sort of structure of reinforcement learning has learned how to play Go, has learned how to fold proteins. And I'm guessing that that similarly, machine learning is going to be very, very useful in trying to understand how to go from phenotype to genotype and back and is going to become a bigger and bigger part of understanding very complex systems like living ones. So, so life and technology, I think, are, with these two technologies independently and combined, entering a sort of new phase, where rather than evolved, life and intelligence will be designed and engineered. And this is just starting, but I think it's likely to be very, very big. And if you think about the numbers, we have a lot of catch up to do. There are of order 10 to the 37 or 38 bits of DNA, bits of information stored in DNA. That's like 10 to the 15 times more than in all the world's digital infrastructure. So that's a big number, that's a big disparity, but it's not as big as it used to be. The computation done by the biosphere in the last 500 million years, I estimated at about 10 to the 50 floating point operations. This is, 27 orders of magnitude larger than the biggest computations that we've done as a species. So we're still pretty far away from replicating what life has done, but as impressive as evolution is, it doesn't have the sort of understanding and self-modeling and reasoning or explicit goals that people have. It's a slow, long process, and it doesn't make the sort of giant leaps in general that intellect and technology can. And so it's very likely that intelligence and not this biological evolution will govern the long-term future of life. And so bringing this back to the eclipse or not in 2522, this makes the very long term very difficult to predict. There are some things that we can say, which are, if we continue with technology, what limits will the laws of physics impose? I think I'd better not go through these given the time. Well, wait a minute, I started this. How much time do I have? Let me ask.
Take the time that you need.
Okay. Okay, so I'll say a little bit about this. So just in some raw numbers, the energy delivered by the sun is 10 to the 14 terawatts. So 10 to the 14 times 10 to the 12 watts. That's delivered by the sun overall. 10 to the 4 terawatts goes to Earth. So that's a lot of power. That's many, many, many times more power than we actually consume in electricity. So there's quite a lot of space to power the world's electricity on solar if we built the solar. And this is a different conversation, but that's solar is now sort of the cheapest way to generate electricity on Earth, not just environmentally friendly, but cheapest. But in terms of long term, this is the sort of energy we have in principle to work with. Coming from the sun. If we were able to just liberate energy directly from matter, like E equals mc squared, that's a huge amount. It's 25 gigawatt hours per gram. So 1 gram of matter could more or less run Moss Landing power plant for a month. If we, I think that's the right number. Yeah, for a month, if we could just turn it directly into energy, and there's nothing impossible about that. So it is conceivable that even more efficient processes than nuclear fusion or fission could exist. So there's just a gigantic amount of information, right? Sorry, of liberatable energy associated with just everyday matter. On the other hand, a human brain consumes 100 watts. It's really quite little. So there's just room for tons and tons and tons of human brains around in terms of energy, or as I said earlier, low entropy energy consumption. Of course, we're not just brains. We've got lots of other needs aside from just our brain. But just in terms of those raw numbers, it's a gigantic amount. In terms of computation, there are limits on how much irreversible computation you can do, called Landauer's limit. It turns out to be 10 to the 19 floating point operations per watt. That is many orders of magnitude more efficient than the computers that we have now. If you combine that with the energy liberated per gram, that's 10 to the 33 floating point operations per gram of matter that you turn into energy. So this is like very, very, very far future technology, but in principle, this is just so much more computation than has been done by all of humanity that could be powered by each gram of matter that we used very efficiently. If it came to it, we have not just the moon that we could turn into computation, but Jupiter is 10 to the 30 grams, the Milky Way galaxy is 10 to the 44 grams. Again, this is a sort of mercenary attitude to take of turning Jupiter into computations. But if we care about the sort of processing of information and think about what humans do and experience and think and so on in those kind of mercenary terms, there's just a lot of capability to do a lot of that in the future, not just time, but huge amounts of computation. And we also have the frustratingly slow speed of light. It's obviously super fast on an everyday level, but irritatingly slow on a cosmological time scale. Years to get to the nearest stars, millennia to get to a typical star in the galaxy. On the other hand, as we saw, we have many, many years ahead of us. And so even if it takes a long time, we can easily, if we go out, colonize the galaxy or beyond with plenty of time to spare before anything really bad cosmologically happens. But there's a way we can screw all this up pretty disturbingly easily, which is to curtail the future of life and humanity here and now. If the AI books don't keep you up at night, here's another thing you can check out, which is the timeline of accidental nuclear war close calls. You can find it on the futureoflife.org website. There have been like 15 or 20 documented ones just from the US side, and we can imagine there are similar numbers on the Soviet or Russian side, where we almost had a gigantic accident, including potentially a nuclear war, and sort of lucked out and it didn't happen. So this is just an awful policy of relying on luck over and over and over again. This is one that will not work in the long term. And yet we're doing essentially nothing about this. We've decided as a culture, basically, well, we've lucked out so far. So therefore, that means we should continue to luck out in the future. But that is a bad idea. It's not the way that luck works or probabilities. And COVID, which is a relatively mild catastrophe in the spectrum of possibilities, has sensitized us to these risks at least, and gives us a window of opportunity. But disturbingly little has been taken from that. If you look at the recent spending bill that's come through Congress, there was a request for $100 million to prevent the next pandemic. They funded $3.5 billion, I believe, which is probably about, 1/1000th of the cost that COVID has had already so far in the world. No, maybe a 10,000th. It's been tens of trillions of dollars, just in terms of costs. So we're not doing so well on this, but there are a number of organizations that are working to improve the probability that life has a future and that future is good. The Future of Life Institute is the one that I'm closely associated with and have helped found. The UC Earth Futures Institute is another one. You'll see that down on the lower right. And then there are a bunch of other ones around the world who are also thinking in this long-term sense and worrying about how absolutely tragic it would be if we curtail this beautiful future that humanity and life could have by flipping off the switch now. There are a few things I think we can do that are fairly obvious. One, and some not so obvious. One is, I think in terms of life, we really ought to save what we have by staving off mass extinction underway. And I think as a backup, sequencing the genome of every organism we can. This is something that I've started to get more interested in. Life has run these like 10 to the 47 operations, and here we are dragging the whole output file into the trash can. Let's try to keep that process running and make a backup of it. Just seems like good caution. We need much better coordination in terms of calling for policy changes related to science and technology in the future beyond the next election cycle. There's just no way that we're going to survive if everyone is only thinking about a time scale of 1 or 2 or 3 or 4 years. Again, we don't all have to be thinking about the long-term future, but somebody should. And some of the most important things that come out of that thinking should need to be paid attention to. We need some real discussion of what we want and not just what we're being dragged inexorably toward by technological progress. We, as a species, have some agency. And the flip side, I think, of this power that's enabled us to destroy the world in terms of nuclear weapons, at least, probably in terms of bioweapons, if we chose to do so, potentially in terms of other sorts of biological, synthetic biology and artificial intelligence. We're now putting ourselves in the position where we can really wreck it all. But there's a flip side of that that is good, which is that if we also have the means, if we use it, to think meaningfully in terms of humanity as a whole and the world and life. And we can ask not, just as in our individual lives, where is it going? We can ask for the species as a whole, and for life as a whole. You can ask these big questions. Where do we come from? What are we? Where are we going? How do we keep it going on? And we've got some decisions to make. And I'll close with this quote from one of my favorite philosophers that I think fits as well now as it did 100 years ago, that people don't sufficiently realize that their future is in their own hands. Theirs is the task of determining, first of all, whether they want to go on living or not. This is both individually and as a species. And then there's the responsibility for deciding if they want merely to live or intend to make just the extra effort required for fulfilling, even on the refractory planet, the essential function of the universe, which is a machine for the making of gods. So that's what I have to say. It's a lot, but I'm happy to stick around and answer any manner of questions.
That was terrific. Thank you, Anthony. Questions out there? I've got a couple, but let's entertain others first.
Can I open the gallery so we can all see each other?
Yeah.
Great.
Well, go ahead, Joel. I think we need to, Joel, unmute yourself.
I didn't have a question. I was just waving hello to everybody.
Oh, okay, great. Well, so I've got an observation and a question. First of all, it was a terrific talk. Thank you. Really thought-provoking. When you described AI and capitalism as single-purpose, systems gone wrong, two thoughts hit me. One is we just discussed capitalism last week, and we saw that. The other is that Congress is one of those. It seems the sole purpose is to get elected and reelected. And it would be nice just to get campaign contributions out. But the other one was this often question of free will, and you sort of call it agency. We've had presentations. In fact, the founder of this group, before I picked up kind of facilitating, was a quantum physics prof who was quite convinced from the physics standpoint, and I think it's probably inarguable, that there is no free will, that everything's a deterministic physical process. But there's another view of that, and that's that, is there a computational energy that can predict or force you to do something? And it used to be 10 years ago when you ran the numbers that there were so many neurons, so many different ways. Imagine you're trying to predict if somebody's going to pick one of 10 blocks, that it would be impossible to have enough bits in the universe to predict what any individual human was going to do with absolute certainty. And I'm wondering if you've updated those numbers. Lots happen in the computational power of the universe, but does that kind of free will exist?
Yeah, so my view on this is there are, as you say, different aspects of free will that you can consider. One among them is the one that you just mentioned. Could an external observer, knowing, as much as it could gather about a neural system, predict what that neural system is going to do at very high accuracy? My suspicion about this is just no, it just can't, in the sense that there are, quantum mechanics provides a fundamental indeterminacy in any physical system, and certainly in the brain, that sort of manifests as the noise that is experienced in the in the neurons and the neural signaling. That noise is real and has consequences. And so I think there is a fundamental randomness to the ingredients of neural processes. I think that if you were able to, suppose I covered up, well, you can't see it anymore, but you had to reproduce the meaning of that Bergson quote. So just produce a paragraph of text that said more or less summarized what that Bergson quote said. You'd write some text. I suspect, although I don't know, and this would be fun to try to figure out an experiment to show, that if you rewound the clock and did it exactly the same, starting in the same quantum state for your brain, and you did it again, I think that text would come out different. It would express the same thing, but the actual word choices have a stochastic component to them that I think would be fundamentally unpredictable as that quantum uncertainty goes through noise, to the effect of these complex processes that are happening in the brain as you make those choices of words. So that's my personal belief. I keep wanting to get a project going on this with at least an artificial neural network, like one of these text generation models, to find out exactly how much perturbation you have to make in the neural weights in those machine learning models to start getting significant differences in the text that comes out, because the text is kind of that comes out as a bit of a chaotic system in that it says some stuff, and then on the basis of that, we'll choose the next word, and then the basis of that, choose the next word. So even a small uncertainty in that can start to compound into a large variation in the text later. So my personal belief is that complex neural systems like us are fundamentally unpredictable. But other people may disagree with that.
Other question, Barry?
So I've heard it described that artificial intelligence at its core is just pattern recognition. And my question is, one, is that true? And another way to put the same question is there additional things to intelligence other than pattern recognition?
Yeah, well, pattern recognition, I wouldn't necessarily say machine learning is the same thing as pattern recognition. You might say it's another pejorative way to put it is it's a big complicated curve fitting. That there's this big sort of complicated function, and you choose a bunch of numbers that can allow you to model that big complicated thing with some big complicated mathematical function of 100 trillion parameters or whatever. Well, 100 billion parameters. And that, at some level, that's just true. That's what is being done, is literally you're fitting 100 billion parameters to this very complicated function that you're trying to minimize. But who's to say that that's not what biological systems are doing too? So their claim would be, or one could claim that what we're really doing when we're learning or operating as a biological creature is somehow fitting the weight, the transmissibility in our synapses to nicely model what the world is doing so that we can then make predictions about it and make choices and so on. So it may be that that's right, but that's not really telling us much, in the same way that you can say a computer is just a bunch of electrons and protons and neutrons moving around. Well, yes, it is, but it's missing out on all the interesting stuff in how large numbers of those things interact. So in terms of pattern recognition, I think there certainly are things other than pattern recognition, and I would say that AI systems are doing that. Depending on what exactly you mean. Like if you look at AlphaGo, for example, it has, it certainly is recognizing patterns in the Go board, but it has a core part that is, trying to decide which move to make by modeling, looking ahead some ways in terms of which moves that it might make and what their consequences are going to be, and assigning different levels of utility and having intermediate goals of like, this looks like a good board configuration, so I want to move toward that. So it's kind of assessing how good is the board that I would get to if I did this choice versus that choice in this big tree of possibilities. So I think, there is pattern recognition in that, certainly, like this looks like a good board position. I'm recognizing that this is a good board position, and that I'm sure actual Go, I'm not any good at Go, but I'm sure actual Go and chess players do some of the same things. But I think it's probably not very accurate to say that's all it's doing. There are lots of different components to what these systems are doing. And I think there's more to intelligence than just pattern recognition. So yeah, I wouldn't say that's, I wouldn't look at it that way personally. I think
Other
they do more.
I have a
Maybe-
question.
Yes, Nancy.
I wonder, where is the Megatron based? Do we know?
That's at Microsoft.
Microsoft, okay.
Yeah, interestingly, Microsoft owns the two biggest language models, Megatron and GPT-3. So although we think of, at least I do, I often think of kind of Google as the big, and Facebook a little bit as the big AI powerhouses. Microsoft is actually a major player in this as well.
How much, how easily accessed is it, or how does one access that, the use of it? Is it heavily?
Yeah, I don't know about Megatron. I do know about GPT-3. So that was developed by this nominally nonprofit organization called OpenAI, but they have a licensing agreement with Microsoft, and you can ask for an access to GPT-3 for various purposes. So you can buy it or sometimes be granted it for research purposes, but it's basically a sort of an API that you can say, I want to use GPT-3, and you pay a fee and you use GPT-3, and then you can use it, you can customize it for your own purposes or whatever. So that one is fairly, kind of a fairly standard, like software as a service model, really. You can pay for it, subscribe to it, use the API. They do have some oversight in the sense that if you just wanted to use GPT-3 to say churn out large amounts of propaganda about some political issue, they would probably notice that and wouldn't let you. But that doesn't mean that other people won't do that with other language models. So there are some real issues with governance of like who is going to prevent some of the not just accidental side effects that I've mentioned, but the deliberate misuse of these high-powered systems, because there are lots and lots of those. I don't know if that's what you're getting at, but I'll get at it anyway.
I've got lots of questions about its use. Yes, I do.
Yeah, good. You should, I think.
So maybe one other point to Barry's question about pattern matching. In the last couple of weeks, there was an article, I can't remember the source, basically bristling at the notion that human decision making had anything to do with computation. And the notion was that we don't really, our memories are not data stores, our decisions are not computations, that it's a little bit more like real-time interaction with the environment. Maybe entanglement would be a sort of noticeable. So for example, when a highly trained baseball player hits a fastball, they're not doing the differential equations, they're doing a dance that they've learned with the baseball. And maybe it is a little bit like dancing, that when Sullenberger lands a plane in a circumstance he's never done before, he's not computing, he's doing, second by second dances with the controls and what the airplane's doing. And I don't know where that goes. I didn't find the article completely convincing, but it does seem that we humans aren't exactly computing our way to decisions. We're kind of interacting with the environment with kind of rules of thumb along the way.
Yeah, I think, well, I have a few thoughts about this. One is, insofar as you think of computation as just information processing, then I think we are, in the sense that like almost everything is doing information processing, including our brains. What exactly, how to describe exactly that information formally, or what it means to be processed, I don't think anyone really knows. But I think in that sense, it's clearly doing computation. what it's just as clearly not doing is the sort of computation that a computer does in terms of memory registers and a CPU and all of that stuff. That is just not a good analogy for what the human mind is doing. But I do think neural networks and recurrent neural networks and reinforcement learning is starting to get much closer to the way the human brain works. If you look at GPT-3 and its ability to do math, simple math, although probably not that much more simple than what people can do in their heads. Like, how many people can add 3-digit numbers in their heads easily? Not that many. So if you look at that, it's a bunch of weights of in the neural network. There's no place that you could find a little statement of what, algorithmically how to add two numbers together, the way you would if you had a operating system that had a built-in addition, that had an addition function, you'd be able to trace, like, here's how it's doing the addition, flipping these bits and shifting these and so on. You'd be able to understand it. There's no looking at GPT-3, I think probably ever, and being able to understand how it's adding up those two numbers. And in that sense, I think it's probably fairly similar to the human mind. You're not going to cut someone's brain open and be like, oh, look, there's the addition part. It's just not there. It's a property of the whole system. So I think, it's true that the brain is not a computer in that sense, but that doesn't mean that it is a thing that whose function can't be matched by some digital neural network, I would say. It still might not be able to. I mean, I think we don't know. The current machine learning systems still are quite far from what humans can do in many ways. But I don't see that fundamental architectural difference being there in the same way. A big difference is the time domain. So most machine learning systems are it's like a big function, you put something in and something comes out. It's just a kind of a static thing. The human brain doesn't work like that at all. Time is very important. So all these cycles that are going on, and the temporal aspect is deeply integrated into it in a way that it's not, I would say, in current machine learning systems. So that's a big architectural difference. But I think the idea that machine learning, that the human brain isn't a computer of the normal digital type, isn't that useful of a observation to make in terms of what AI will and won't be able to do.
Thanks. Other questions? Mark, you have any? Hugh?
Mhm.
Oh, I do. I have one. So Anthony, that was fabulous. What a great talk. So provocative. Is it possible for AI to have judgment? And I don't mean moral judgment, but just judgment based on factors like what will be good in the very long term for more people. I mean, can it make that kind of a judgment?
Well, at the moment, I don't think it could be sent to. I think it all depends on yes and no, in the sense that it's certainly true that if you took a big data set of human judgments about stuff and trained a modern AI system on it, it would be able to sort of at least provide a facsimile of judgment in itself. So there's a system that came that was just put out by the Allen Institute on morality. So it's a moral system that's trained on a bunch of human moral statements, and you can ask it moral questions, and it will give you answers to them, many of which will probably match what people would say, and then many of which it's like very easy to trip it up, and it will say totally wrong things. So it's fragile, but it is doing it, right? So if you give it this training data, it will kind of learn how to emulate what that training data is doing. To what degree that is the same thing as doing that thing probably varies from place to place. I mean, if you think about a lot of the decisions we make, they're more or less by habit, or like kind of how we've done it a million times before, or how we've seen other people do it. So we're not so different. But we do have a much better ability to step back and say, let me try to understand the reasoning. Let me understand what my motivations here are. Let me pick this apart, and think about it. And I think at that level, machine learning systems right now are not doing that, not at all. But whether they will someday, I don't think we know.
Any other questions?
Lots, but they would take.
Right.
Yeah, I think I have to agree with the system that Nancy's saying. This was a terrific talk. Really gave us a lot to think about it, and I guess we've either gained or lost an hour more to think about it. So we'll go there. Anthony, thank you so much. This was really great.
It's a pleasure to be here.
Really appreciate it. Joel, thank you for recommending him. Yeah. All righty, we'll catch you all later. Cheers.
Take care, everyone.
Pete, quick question. Do we have well, December and January, what's the
So
lineup?
we have a speaker for January. December is up in the air. We may be having a holiday break, or we may get a speaker.
Okay, and not beyond January. Yeah.
That's correct.
Okay, I have some ideas. We can
All right,
talk.
great. That'll be good. Excellent. All right.
Right.
Cheers, all.
Thank you.
Bye-bye.
Bye-bye.
Recording.